You know, in physics, the idea of work seems pretty straightforward at first. But what happens when the real world gets a little messy? What if the force you're dealing with is constantly changing? Well, that's where things get really interesting, and that's where calculus becomes our superpower. Let's dive in.
So we all start with this one, right? Work equals force times distance. If you're pushing a box across the floor with a steady force, this is all you need. It's the bedrock. But as we're about to see, it's a foundation that can only handle the simplest of problems.
Because let's be honest, in the real world, force is hardly ever constant. Think about stretching a spring. The more you pull, the harder it pulls back. Or what about lifting a heavy chain off the ground? As you pull more of it up, the part you're lifting gets lighter. So, how do you calculate the work for that? Well, the answer, my friends, is calculus, specifically integration. See, the brilliant insight here is that we can take a big, complicated task and break it down into an infinite number of teeny, tiny, simple tasks. That's the core idea that's going to let us solve all these problems. And here it is, our elegant new tool. Instead of just multiplying, we're now using an integral. And what this lets us do is treat our force, F, as a function that can change depending on its position, x. This one little formula is the key that unlocks everything we're about to do. So here's how to think about it intuitively. We're chopping a big, hard problem into an infinite number of little, manageable pieces. And over each of those tiny, tiny little pieces, the force is basically constant. Then, the integral just does its magic and adds up the work for every single one of those little pieces for us. All right, let's put this into practice. Time for our first challenge, stretching a spring. This is a total classic when it comes to calculus problems, and it all revolves around a pretty simple rule from physics called Hooke's law. So, what is Hooke's law? It just says that the force you need to stretch or compress a spring is directly proportional to how far you stretch it. F equals kx. That little k there is the spring constant. It's just a number that tells you how stiff the spring is. A bigger K means you've got a stiffer spring. Simple as that. For basically any spring problem, we're going to follow this simple three-step game plan. First, we use the info they give us to find that special number, K. Then, we build our work integral. And finally, we just solve it to get the answer. Ready? Let's do it. Okay, step 1, find K. The problem tells us that a 10 Newton force stretches the spring 0.1 meters. So we just plug those numbers right into Hooke's law. A tiny bit of algebra later, and we can see that K, our spring constant, has to be 100. Step 2, let's set up that integral. We now know our force function, f of x, is just 100 times x. And the question asks for the work to stretch the spring from its natural length, that's x equals 0, to a new length of 0.2 meters. And just like that, we have our bounds of integration, from 0 to 0.2. And when we actually calculate that definite integral, we get our answer, 2 joules. That is the total amount of work it takes to stretch this specific spring by 0.2 meters. And just like that, we've crushed our first variable force problem. Okay, time to level up. Our next problem is a bit more complex. Here, we're not just dealing with a force that changes, but with a situation where different parts of an object, in this case little slices of water, all have to travel different distances. Let's see how our integration strategy holds up. The core strategy is actually exactly the same. We're going to mentally slice the water in the tank into these infinitely thin little horizontal discs, like a stack of pancakes. Then, we'll figure out the work it takes to lift just one of those discs to the top. After that, the integral will do the heavy lifting of adding up the work for all of them. So for each one of these imaginary water pancakes, what do we need to figure out? Really, just two things. First, we need its weight, which is just its volume times the density of water. And second, we need the distance that specific slice has to travel to get pumped out of the tank. So let's apply this to a real example. Picture a big cylindrical tank. It's got a radius of 2 meters, and it's 5 meters high. It's filled to the brim with water, which we're told has a weight density of 9,800 newtons per cubic meter. Our mission is to figure out the total work needed to pump all of that water out over the top edge. Now we get to the trickiest part, the part where a lot of people get tripped up, defining the distance. If we set up our coordinate system so that y is the height of a slice from the bottom of the tank, then the distance that slice needs to be lifted to get to the top is the total height, which is 5, minus its current height, which is y. And I know what you're thinking. Why is it 5 minus y? Why isn't the distance just y? That feels way more intuitive, right? This is a super common point of confusion, so let's clear this up right now. It all comes down to where we put our starting line. We decided to say that y equals 0 is the bottom of the tank. That means the top is at y equals 5. So think about a slice of water that's already 1 meter off the bottom. Does it need to travel 1 meter? No, it needs to travel the rest of the way to the top. That's 5 minus 1, which is 4 meters. The distance is the destination minus the starting point.
Okay, now we can build our integral. Our bounds go from 0 to 5 to cover all the water. The distance term is that 5 minus y we just figured out. And the force? Well, that's the weight of each slice. The volume of a little disk is pi times radius squared times its thickness, dy. So that's pi times 2 squared times the density of 9,800, which gives us 39,200 pi. Put it all together, and you get this integral right here.
All right, let's tackle our final challenge, lifting a heavy chain. This one is a lot like the water problem because, again, different parts of the object are going to move different distances. But the setup is just a little bit different, and it's a really good one to know.
So, here's the scenario. We've got a 10-meter-long chain that's just dangling from the edge of a roof. We're told it has a linear density of 2 kilograms per meter. The goal is to find the work required to pull the entire thing up onto the roof.
Now, for this problem, let's actually change our coordinate system. It makes way more sense to set y equals 0 at the top of the roof this time. So if you think about it, a little piece of the chain, dy, that's already at a position y down from the top, only needs to be lifted, well, y meters. The piece at the very bottom at y equals 10 has to travel the full 10 meters. See how that simplifies things?
So let's build this integral. Our bounds go from 0 to 10 to cover the whole chain. The distance to lift a little piece at position y is just y, and the force, or weight, of a tiny piece dy is its mass times gravity. The mass is the density, 2, times its length, dy. So the force is 2 times 9.8 times dy, which is 19.6 dy. Integrating 19.6y from 0 to 10 gives us our final answer, 980 joules of work.
So there you have it. We've seen how to handle forces that change and objects where every piece moves a different distance. The core technique is always the same. Slice the problem up and let the integrals sum it up. But here's a final challenge for you to think about. What if you were lifting that same chain, but attached to the end was a bucket that was leaking water at a constant rate? Now, the mass itself is changing as you lift. How would you solve that? Thanks for tuning in.